Okay, now, what else can you do? Well, suppose that a derivative were to be 0. Well, how could that possibly happen? That could possibly happen because maybe the function goes like this, and I see the tangent over here has slope 0. Or maybe the function goes like this, and I see the tangent has slope 0. In particular, if the tangent equals 0, maybe we have a max or min. Also, maybe the slope or the tangent doesn't exist. Like if we have a wave kind of thing, a cusp, very pretty cusp like the waves. Well, that might be a max, that might be a min. So in particular, you can find out when objects are maximized or minimized. You can find the maxima or the minima very easily by using calculus. What do? You take a derivative and you see where it equals 0, or where the derivative doesn't exist but the function does. Those give you candidates for possible max and min. And what can you use that for? Well, you can do all sorts of now max-min problems. You want to maximize profits, you want to minimize cost. Oh my God! 20 minutes? No. It's only 10 minutes left. They're trying to fool me here, folks, but I'm not going to go up for it. 10 minutes are left. Okay, so you want to maximize cost, you want to minimize cost, you want to maximize profit, you want to maximize area, you want to minimize volume, whatever it is, set up the problem really carefully, figure out exactly what you want to optimize, take the derivative, set it equal to 0, solve, find out where the derivative is undefined, and you've got it made. Really not a big deal. However, you should always remember and never forget the fundamental method of solving problems. So remember how you solve all of life's problems. The first thing you have to do is understand what you're being asked. You can't answer a question that you don't understand. The next thing you do after you understand what you're supposed to find, what you're being asked, is figure out what you know. List every single thing that you know, every single fact. Maybe superfluous, maybe you don't use it. Who cares? Write it down, understand it, make it your own. And then the last thing is take the information that you know and see a relationship between that and the thing that you seek. Try to find a connection. Once you got the connection, then you're on the road to actually finding the solution. That is the simple method for finding any single answer to any single problem. Another application, if we think about derivative as a rate, is looking at related rates. Suppose, for example, that you actually have a ladder, for example, that's falling down. The ladder is falling, and you don't want to be sued, but the only thing you do know is how fast the bottom is falling. You want to know how fast the top is falling. What you need to do there is if you know this rate, you can find that rate by linking them up with a connection. In this case, a connection would be the Pythagorean theorem. You could take the derivative with respect to time, because here you see the variable, the thing that's independent, that's always changing, is time. Time keeps on ticking into the future. So you keep going like this. You actually solve this, take the derivative using implicit differentiation, differentiate with respect to time, and plug in what you know how this is changing, and that actually tells you how this is changing. Pretty cool. That's called implicit, that's called related rates. Suppose, for example, you drop a stone into a very, very still pool. You have a ripple effect. Those make concentric circles that are getting larger. If you know how fast the radius is changing, you can find how fast the area is changing because you have a connection between area and rate. Area equals pi r squared. So there you go, related rates. If you know how one rate is changing, you can find out how a related rate is changing. Okay, what else can you use the derivative for? Well, the other thing you can do is actually graph really, really accurate pictures of functions. Finally, you can figure out that a parabola looks really pretty and bowl-like, like this. And it's not something really exotic, but it's just a nice pretty bowl. How do you do it? Well, you just start taking derivatives and analyzing things. First, you find the critical points. Those are points where the derivative either equals 0 or where the derivative is undefined, but the function is defined. So, for example, in these examples right here, you'll notice that the derivative equals 0 here. The tangent is horizontal right there. The tangent is horizontal here. In this example, the tangent is horizontal here. And then where does the derivative not exist? The derivative doesn't exist here, and the derivative doesn't exist there. Those are candidates for max and min. Those are called critical points. Then what do you do with those things? Well, you set them up on a little number line on the x-axis, and you look at the intervals all around it, and you see whether the derivative is positive or negative. If the derivative is positive, that means slopes are positive, so the function must be increasing. If the derivative is negative, then that means the function must be decreasing. So you can see that the function, for example, here is decreasing, 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 then increasing. Here you can see it's increasing, 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 then decreasing, then increasing. So you can see where it's going up and where it's going down by the sign of the first derivative. That also determines whether you have maxes or mins anywhere, and that's called the first derivative test. Now, how do you figure out the curvature? The curvature is given by the rate of change of the derivative, how the derivative is changing. So what you do there is you take the derivative of the derivative. So you look at the second derivative, and that where the second derivative is 0 are potential points of inflection, points where the concavity changes. This is concave up, it's curving upward. This is concave down, this is concave up. So the cup is sitting up, the cup is sitting down, concave down. So here you would see the second derivative is positive, then the second derivative is negative. It changes here. Now it's sitting up. It's positive, positive. We're concave up. Here we're concave up. Second derivative is positive. Now here we see it's concave down. Second derivative is negative, and second derivative here is also negative. This is a cusp point. The derivative doesn't exist there. This is a point of inflection. This is a point of inflection. This is a point of inflection, and that's a minimum. So just by taking derivative and then second derivatives, you can actually figure out and graph a very accurate sketch of even very complicated, almost scary-looking functions. By the way, if you've got fractional exponents, expect cusps. That's my warning for the day. Okay, now, if you've got really exotic functions that have denominators, then actually you may have asymptotes. So don't forget that a vertical asymptote is where the function, after you simplify it, the bottom equals 0. So wherever the bottom equals 0, after you simplify and reduce, those are going to give you your vertical asymptotes. Horizontal asymptotes, you take the limit as x goes off to infinity, as you go off to the horizon, and you see what y value you're trying to land to. If you're landing somewhere, then you know you've got a horizontal asymptote, and it's at y equals that value. So you can put in the asymptotes, and then you can do all the other calculus, get the curvature, see exactly what the beautiful picture looks like. And that was the end of differential calculus. Great, no problem. Now what? Well, now we move on and look at the exact same thing we just did backwards. So we look at Math Jeopardy. Oh my goodness, I have only 5 minutes left. So Math Jeopardy, here we go. So the idea is, if I tell you what the derivative is, how can you find the function whose derivative is that? Well, this is the notion of an antiderivative. So how do you actually find antiderivatives? Well, we saw the formulas for that. If you want to find the antiderivative of x to the n, it would be x to the n plus 1 divided by n plus 1. Take the derivative of that and see you get x to the n. Unless n equals negative 1, then you're looking at the integral of 1 over x. And what's the integral of 1 over x? Well, it's the natural log of the absolute value of x, because the derivative of natural log we already saw was 1 over x. So great. Now, how can you find exotic integrals? Well, remember that d dx represents differentiating with respect to x, and so therefore the integral with respect to x represents to integrate with respect to x. Now, if you have a very complicated thing there with an inside and outside, you might be able to untangle that, which potentially was made by the chain rule, by using substitution. Let u equal some big blop, and the big blop's derivative should appear somewhere else in your integral. If you've got that, it sounds like a good candidate for u du substitution, and then you've got to change the dx to du by taking derivatives and seeing what du equals in terms of dx. So that's the u du substitution. You got that going on here. And now what you can do, you can take that and look at studies of motion again. Now I can give you acceleration. If you integrate, you get velocity. If you integrate again, you get position. So vertical motion, not a big deal anymore. Lands, no problem. Things moving in space, like this thing here. Watch it, folks. Woo! You can get that. You can anything that moves, anything at all that moves, we can now analyze whether you have crabs or whether you have a bike. It's not a problem anymore, folks. If it's movement, we can antidifferentiate it and figure out what it is. Not a problem. Now, where does this lead us? Well, it brings us back to the very first question of the course, which was, how do you find areas under curves? We have to answer that. We haven't done it yet. It turns out the surprising answer is that it's the fundamental theorem of calculus. And the idea is, if you want to find the area under this curve from A to B, right here, if you want to find that area, then how do you do it? It turns out that if that function is called, let's say, f of x, then all you do is integrate from a to b f of x dx, because you're summing up little rectangles in here that are base, small change in x, base times height, which is the function. You go from a to b, and this equals f of capital F of b minus capital F of a, where what's capital F? That's the antiderivative. So if you take the derivative of capital F, you actually get little f of x. So just find the antiderivative, plug in the big point, plug in the small point, subtract. That will always give you the area under the curve. You could look at areas of more exotic things. For example, if the thing actually goes like this, then actually, this is actually not very x-easy. The rectangles aren't very clear. The rectangles change from going from green to green, over to green to orange, then to orange to orange. It's not very uniform. However, if you put the rectangles in this way, and stack them this way, now you're summing with respect to y. And so here you would actually sum this with respect to y. So you would integrate this dy and put the rectangles in this way. And you put the rectangles in that way and stack. You'd stack from low to high, and you'd stack the rectangles like this. Okay, that is all of calculus. I did it in under 20 minutes. That's what it is. Go back, think about it, have fun with it. Congratulations, folks. You just finished Calculus 1. Have a good time. Celebrate. Good luck in the final. Bye.